Okay, everybody. My name is Nico. I'm a software engineer at Cruise Automation, where we'll be building self-driving cars in San Francisco. This short talk is basically going to be about lessons that we learned using basically the ROS framework to actually build those self-driving cars. Just to get started, we have a fleet of around, it's cutting a bit of the text, sorry guys. We have a fleet of around 100 self-driving cars that drive around San Francisco, of course with safety drivers, and a team of 500 software engineers that write the code for those cars. More technically, just to give you an idea of the complexity of the problem, we have a sensor suite that has like around 10 cameras, a bunch of LiDARs, radars, of course IMU, wheel sensors, and all of these sensors together produce around 1 gigabyte per second of data. So it gets pretty complex. And it's actually amazing that the first Git commit in the history of the project actually had already ROS in it. And it's amazing how far we have been able to scale it up, both in terms of like software and in terms of people. So today I basically, everybody knows what ROS is good. So today I'm going to actually go in and like talk about sort of like the boundaries, right? What's actually hard to do and the areas where we have had to push a bit over what's available and to basically achieve our goal. So I'm going to be talking about some problems around determinism and simulation, then some stuff we constantly fight with on the core framework side, and then also some nice developer tooling that we've built. So let's get started with simulation. Simulation is important, especially when you make mistakes in your software and they kill people, which is not nice. So of course, testing on real cars, it's complicated, it's expensive. We have a good process, but still it takes like 2 humans to like drive a car around and collect data. So you would think this is pretty easy, right? So we use ROSpec, we record all the data as we go, and then we spin up a bunch of cloud machines, we use ROSpec Play, and then we run the simulations. Except this doesn't really work well for an expensive system, right? Basically, the only thing that ROS gives you in terms of simulations is the ability to play back the sensor data, basically cutting out the drivers and like replaying the sensors. Optionally, you can reproduce your clock as well using simulated clocks, and supposedly that enables you to run the same robotic system without actually access to the robotics hardware. However, there's like 2 big issues with that. One is that on slower hardware, which is very likely, right? You have a very expensive CPU on the car, but you have a cheaper cloud machine to run your tests and simulation. If you're on slower hardware, you have to slow down the replay, or you end up missing frames, which sort of destroys the point of simulation, right? And the second problem is that all of this data still goes through the same ROS pub/sub mechanism, right? So you get all these weird timing and sampling effects, and determinism goes out of the window. Determinism being defined as given the same inputs, you get the same outputs, which again is pretty important for simulation, as you can imagine. So what did we do at Cruise? First, we learned that like simulation is really important, and it should be like a first-class concept on any robotics frameworks, basically, because otherwise it's really hard to make progress. So basically, the goal would be to achieve deterministic, lockstep simulation, starting from recorded data, from ROSpec data. And we basically did it in sort of like 3 conceptual steps. First, we took out some flexibility in the pub/sub model, which basically allow us to have like more information about what the computational graph looks like. Once you have that, you can actually control, deterministically control when computations takes place by controlling the data flow across the nodes. And finally, you build some sort of acknowledgement system so that basically you know when like a node is done computing given a set of input data. And there's like a big team working on this, so it's definitely not solved yet. Second part of the talk is going to be some stuff that we run into on the sort of core framework stuff. The way you write code in ROS is that you need new functionality, so maybe you spin up a new node, eventually maybe you move into a nodelet. If your system is actually loaded, and we have like a lot of CPU cores, your Linux OS then becomes very confused because it has like thousands of threads to schedule, but it only has like a few dozen CPU cores. So which thread gets to run? And of course, you can do a lot of work on like kernel level scheduling and stuff like that. But the core problem remains that this adds like a lot of worst case latency to the system. You get like latency spikes, timing issues. And we mostly work around it by basically pinning threads to cores and like stuff like that, but that's not really nice. A second problem on the sort of like framework stuff is that ROS basically shuffles messages around, but it doesn't really give you like a nice way to keep track of what those components are actually doing with the data. So you can't really track where your CPU time is spent. And typically this shows up as some downstream component is late, and you don't really know where in the sort of like upstream stack the problem actually is. So we built some tooling around the Chrome trace viewer that basically allows you to visualize some sort of flame graphs throughout the system. And we also basically extended sort of the ROS CPP API so we can pass up contextual information that can collect runtime samples about the data. And this is basically what it looks like, and you can see basically different threads of execution. There could be multiple cores, and then like a flame graph of basically where the CPU time is actually spent, and some sort of like latency measurements. The last sort of area I want to talk about is developer tooling, basically. When you have 500 engineers working on a problem, like any sort of like little like problem that you have is basically a loss of wasted time and money, right? So we try to basically polish what's already available in the ROS community. The first thing is about like ROSbag, recording data. Of course, you need a lot of data basically to develop these machine learning algorithms, right? And bags are good for logging. They just stream the data directly from ROS CPP, but the file format is not really good for like big data stuff. And ROS serialization is really not nice when you develop a system over time, because as soon as you change the message definition, you need to basically process all the data again because you cannot read it anymore. And there's really no nice way around this. We had to build like a lot of like data infrastructure to basically sort of work around this problem and allow us to do sort of like batch operations on like a ton of data that we collect over time. A second point is that like the sort of ROS ecosystem comes with like a lot of nice GUI tools like RQT, RVids. They're very flexible, but they need sort of like a Linux workstation running with ROS. And they're so modular that there's like a steep learning curve to them. So what we did at Cruise was creating sort of like a more monolithic but still customizable web interface for this, so that you can basically just connect and stream data. And finally, a bit about the build system. Of course, we have a lot of CPP code, and C++ is really slow to compile. On top of that, Catkin is really modular, so it needs to do like a bunch of configuration every time. At Cruise, we switched over to Bazel, which is basically the open source version of the internal build system that Google use. And that basically allowed us to build most of our stuff from source, avoiding like a lot of like weird linker issues and stuff like that, but still use the shared cache to spin up both our builds in CI and basically the daily developer workflow. I think I'm right on time, so thanks a lot. And if you have any questions?
We could probably take one question. Sir Doug.
Yes. Yeah. Sorry. Yes. Any plans to open source some of the WebViz? Yes, there are plans underway to do it. We just need to split up some proprietary stuff as always. But yeah, it's nice. Works over WebSockets, so you basically have some sort of WebSocket component, which is nice. So you can do it over the internet and it can be secured properly.
I have a question about the determinism layer for
Yes.
simulation. Is that also open sourced?
No, this is so mixed up with like our own concerns that it's probably really hard to open source, I have to say. But probably some of the ideas can be reused, I guess. I mean, of course, I'm not speaking for the company. That's sort of my own opinion, but I see it very hard.
All right, thank you.
I think we'll have to stop it for 10
Okay,
minutes.
cool. Thanks.